Hi and welcome to John's Maths book. In this video, we're going to be finding the area of a rose petal bounded by a polar curve. If you like the video, then please hit the like button and I'd be delighted and honoured if you'd subscribe to the channel. Without further ado, let's go over to the whiteboard. Let's look at how we find the area of a polar region shaped like rose petals. To do this, I've sketched the polar graph of r equals 2 sine 2 theta. Before we find the area, let's get a better understanding of polar curves using a graphing tool. I've plotted the polar region of r equals n multiplied by sine k theta, and I've set n to be equal to 2 and k to be equal to 2. This gives us the polar region in our example. Note here that n denotes the length of each petal, and in our example, the length of each petal is 2. Let's change the length n to be 3 and see how it affects the region. Now n is set to 3, and as you can see, the length of each petal in the polar region has increased to 3. I've now changed n to be negative 3. As you can see, the region still has 4 petals, and the length of each is 3. So the rule here is that the length of a petal is the absolute value of n. Let's now look at the value of k. In our example, we have a value of k equal to 2. Note that 2 is an even number and we have 4 petals. I've now changed k to equal 3, and as you can see, we now have 3 petals, which is equal to the value of k. Note that this time k is an odd number. Now let's increase the value of k to 4 and see how it affects the region. With k set to 4, an even number, our polar region has 8 petals. So the rule here is if k is an odd number, our region will have k petals. If k is an even number, our region will have 2 times k petals. Now we have a better understanding of our region. Let's look at how we find its area. We know that the area across a polar region is given by the double integral across the region of infinitesimally small slices of area, which we call dA. This translates to the region being defined by an inner integral which integrates in the r direction between 2 values of r, and an outer integral which defines the region as we rotate about theta between 2 values of theta. The infinitesimally small pieces of area are defined by rdrdθ. So for the inner integral, we can see that it begins at the origin where r is equal to 0 and extends out to the polar curve, so where r is equal to 2 sine 2 theta. To find the limits of theta, let's look at how the polar region is plotted using the plotting tool. I'm now going to trace the polar region along the orange dotted line by varying the angle of theta. The plot begins when theta is equal to 0 and r is equal to 0. When theta reaches 45 degrees, r is equal to 2, and we have plotted 1/2 of a petal. 1 petal is complete when theta is equal to 90 degrees or pi by 2 radians. As I increase theta to 180 degrees or pi radians, I've now plotted 2 petals. Continuing, we see that all 4 petals have been plotted when theta equals 360 degrees or 2 pi radians. So, to manually determine the integration limits of theta, we can use the equation of the polar curve where r is equal to 2 sine 2 theta. For the lower limit, we set r equals 0 as the curve begins at the origin. If we now solve this equation for theta, we can start by dividing both sides of the equation by 2 to leave 0 equals sine 2 theta. We then ask the sine of what angle when multiplied by 2 gives 0. The answer to that is 0. So our lower limit of integration is where theta equals 0. We also saw that when r was equal to 2, 1/2 of the petal had been plotted. So let's determine what value of theta we're at when r is equal to 2 by plugging in the value of r equals 2 into our polar equation r equals 2 sine 2 theta. Dividing both sides of the equation by 2 gives 1 equals sine 2 theta. So now we ask the sine of what angle when multiplied by 2 gives a value of 1. The answer to that is 45 degrees or pi by 4. as when multiplied by 2 gives 90 degrees or pi by 2, and the sine of pi by 2 is equal to 1. So 1/2 of a single petal is plotted between theta equals 0 and theta equals pi by 4. To determine the value of theta that completes a single petal, we could use the fact that the petal is symmetrical and just double the angle of pi by 4 to give pi by 2. Or we could use the knowledge that one complete petal is generated when r returns to the origin and therefore is equal to 0. So using our polar curve, r equals 2 sine 2 theta, and setting r equals 0, we have 0 equals 2 sine 2 theta. If we divide both sides of the equation by 2, we have 0 equals sine 2 theta. We then ask the sine of what angle, when multiplied by 2, gives a value of 0. And the answer to that is pi by 2. Because when we multiply it by 2, we get pi, and the sine of pi is equal to 0. And therefore 0 is shown to be equal to 0. And so, to find the area of a single petal, the limits of integration for theta are from theta equals 0 to theta equals pi by 2. And to find the area of all 4 petals, we can multiply this double integral by 4. Let's now begin to evaluate this double integral. So starting with the inner integral, we have the integral from r equals 0 to r equals 2 sine 2 theta of r dr. So the antiderivative of r is r squared divided by 2, and we need to evaluate that between 0 and 2 sine 2 theta. So if we plug in 2 sine 2 theta for r, we have 4 sine squared 2 theta divided by 2. And if we plug in 0, we have minus 0. So this gives 2 sine squared 2 theta. And now moving on to the outer integral, we have 2 multiplied by the integral from theta equals 0 to theta equals pi by 2 of sine squared 2 theta d theta. So now, using a double-angled trig identity, we can convert sine squared 2 theta to be equal to 1 minus cos 4 theta divided by 2. Multiplying through by 2, we now have the integral from theta equals 0 to theta equals pi by 2 of 1 minus cos 4 theta d theta. If we now integrate term by term, the antiderivative of 1 d theta is theta, and the antiderivative of minus cos 4 theta d theta is minus sine 4 theta divided by 4. Evaluating theta between 0 and pi by 2, we have pi by 2 minus 0, and then evaluating minus sine 4 theta divided by 4 between 0 and pi by 2, we have the sine of 2 pi divided by 4 minus the sine of 0 divided by 4. The sine of 2 pi is 0, and the sine of 0 is 0. So we're left with pi divided by 2. This gives us the area of one single petal. To get the area of all 4 petals, we multiply through by 4. So we have 4 multiplied by pi by 2, which is equal to 2 pi, which is our final answer.